Hello and welcome to the 21st lecture in this series. Today I'm going to talk, we'll continue where we had stopped last time. And now that we have the notion of a smooth map, the derivative of a smooth map, and we know that the dimension of the tangent space is what we expect it to be, we can carry over several of the most important results in the Euclidean case to the case of manifolds. So in particular, let's state the inverse function theorem for manifolds. So here the setting is let f from Mn to Mnn. So the point is that both M, the domain manifold and the target manifold should have the same dimension, be a smooth map. If let P belong to M and suppose that DFP from TPM TF of Pn has rank n. In other words, DFP is invertible. It's a bijective linear map. That's the as rank n. Then there are neighborhoods U of P and V of f of P such that V is the image of U and f from U to V is a diffeomorphism. In other words, f from U to V is bijective and the inverse of f is smooth as well. So this is exactly the direct generalization of the classical inverse function theorem. And similar, whatever we had corollaries we had in that setting, they continue to hold here. So corollary if and DFP, rank of DFP equal to n for all P in M, then f of M is an open subset of n. Argument for this is exactly the same as what we had for maps between open sets in Euclidean spaces. And the second thing we had in that setting was that if f from Mn to Nn is smooth, bijective, and rank DFP equal to n for P in M, then F inverse from N to M is smooth. So again, the proof is exactly the same as what we have for the classical this inverse function theorem. Now, as for the proof of the inverse function theorem for manifolds, so let me just make a few remarks. Proof of the inverse function theorem so this is M, this is N, and I have a map F. P is a point here, F of P is a point here. The conclusion of the inverse function theorem is a local one. In other words, we are asserting the existence of a neighborhood of P and a neighborhood of F of P. So we are not saying anything about the behavior of F globally, which is not surprising since the assumption of the invertibility of the derivative is only at the point P. So because of this local nature, what I can do is I start with a chart here. Let's start with some chart here. I'll call it some X phi be a chart. So this is my X around P. And I would like to choose a chart here, Y. Chart around YC, a chart around F of P. So essentially I would like to reduce to the Euclidean case. The only thing is that, as usual, so I would want to have F of X, the image of this open set X. I would like it to be contained in Y. And we know that we can always achieve that just by taking, we have seen this before, even in the definition of smoothness, this issue arises by considering the open set F inverse Y intersection X. We can assume that F of X is actually contained in Y. This is not an issue. So once we have that, perhaps I should have left some space there. So this was my X, P, F of P, and this is the chart Y. And I know that F is taking this open set to this open set. Since this is a chart, I have this map phi here, C here. Let's call it X1 and Y1. These are X1 and Y1 are open subsets of Rn. Well, so far I have not used the hypothesis on the derivative. This is just a general thing. And then now what I do is consider the map F in these coordinates. In other words, I look at phi inverse composed with F composed with C. That's a map from X1 to Y1. The point P, let's say this goes to Q. Q equal to phi of P. Now, the fact that we would like to say, so let's call this map as some map G. So note that rank DG Q is equal to N. This is because, well, since DGQ, it's a matter of G is this composition of three maps, so I just apply the chain rule. So first I have D phi inverse at the point Q, and then phi inverse is going to take me to DFP, and then DC at f of p. And well, we know that by definition almost that this phi and C, the chart maps, are actually diffeomorphisms. So, and we also know that when we have diffeomorphisms, the rank of the derivative is the full rank. So, in other words, the derivatives are linear isomorphisms between corresponding tangent spaces. So, and D phi inverse at Q, D phi at f of p are isomorphisms. So these I'm basically, this dg at q and df at p are related by precomposing and postcomposing by isomorphisms. Therefore, they have the same rank. That's what I'm claiming here. And then the classical inverse function theorem. Inverse function theorem for open subsets of Rn gives neighborhoods let's call it A of Q and B of, well, it is C of f of p. So this point is C of f of p. Such that G from A to B is a diffeomorphism. So once we have this A and B, then we just pull them back to the manifolds and we get the corresponding statement. So A would be this, and so this would be A, this would be B. So what I do is I just take phi inverse of A. It will give me a smaller subset here. This is phi inverse of A. And likewise here, I'll take C inverse of B. That will give me some small open set around f of p. It is clear that f from phi inverse A to C inverse B is a diffeomorphism. And this is what we are going to call. So recall that in the statement of the inverse function theorem, what we asserted was that there are open sets neighborhoods u of p and v of f of p. So we just call these two things as u and v, and we are done. So likewise, we also have the constant rank theorem, which again the proof is exactly similar. Given the Euclidean statement, you just reduce it to the Euclidean, using the Euclidean constant rank theorem, one can get this. So let me just state it. Constant rank theorem. Now we don't assume that they have the same dimension. Be a smooth map. Suppose that there is a k greater than 0 such that rank DFP equal to k for all p in M. Then at any, if P naught belongs to M, there are charts U phi of P naught and VC of f of P naught such that phi inverse composed with F composed with C. This would be a map from phi of U to C of V. Here before I make this statement, as usual, I want to say that the first thing is such that the small condition that f of U contained in V and this map from here to here has the form C composed with F composed with phi inverse of x1, x2. So let's assume that dimension here is n, dimension here is m. So x1, x2, xn is just x1, xk 0, 0, 0. As usual, as in the Euclidean case, if these zeros may not occur depending on the whether m is greater than n and what k is. So these zeros may or may not occur, and in fact, so the proof of this follows from the Euclidean constant rank theorem. So as in the Euclidean case, there are three important classes of maps. One we have already seen, the notion of we have a diffeomorphism between two manifolds. The other two classes of maps, well, actually apart from diffeomorphism, there is in terms of diffeomorphism of a map involves not just condition on the derivative, but rather that the map itself should be bijective. Solely in terms of the derivative, there are three classes of maps. In terms of derivatives, there are three important cases of constant rank maps. So here I don't need capital letters of constant rank maps. The first one is I have f from m to n here the first condition is that DFP is invertible. So i.e. dimension of M equal to dimension N equal to rank of DFP. In this case, F is said to be a local diffeomorphism. And the terminology is clear enough because this is the setting for the inverse function theorem. The inverse function theorem tells us that there, given any point here, can find an open set or an open neighborhood which is diffeomorphically mapped onto an open subset of the image point, open neighborhood of the image point. So therefore we have this name here, local diffeomorphism. The other one is F from M to N. DFP is, oh, here I should mention that DFP is invertible for all P in M. DFP is injective for all P in M. In this case, we say that again, this will force, we say that F is an immersion. So in this case, this will force, note that dimension of M should be less than or equal to dimension of N. Because after all, the DFP is a map between tangent spaces. So DFP is a map from TPM to T F of Pn, and if this map is to be injective, then the dimension of the image vector space is at least the dimension of the domain vector space. These vector spaces have the dimensions equal to the corresponding manifolds. The last case is when I have DFP is surjective for all P in M. Here we say that F is a submersion. In this case, dimension of N. So again, the tangent map, the differential would be a map between two vector spaces, and we are claiming that the assumption is that this is surjective. Therefore, the dimension of the image vector space should be less than or equal to dimension of the domain. And it translates to a statement about the manifolds. So dimension of N less than or equal to dimension of M. Right. Now let me quickly give an example of a smooth map between from R2 to R2 to illustrate this the difference between a local diffeomorphism and an actual diffeomorphism. So let F from R2 to R2 be f of xy equals e to the x cos y e to the x sin y. So this, you can recognize that this map is nothing but the map f of z is e to the z in complex coordinates. Here I have just written it in Euclidean coordinates. Well, this map is F is a local diffeomorphism. So in other words, the derivative of F is invertible at all points in R2. So to see that, you just write down the derivative. We know that the derivative, the notion of derivative is the same. The two notions of the abstract notion of derivative and the classical notion of derivative are related by isomorphisms. Therefore, when we talk about rank, we can work with either one in the Euclidean setting. So here I'll take the classical derivative, and the classical derivative, the matrix of that is just the Jacobian matrix, e to the x cos y, e to the x sin y, e to the x sin y, and then minus, well, so here I should get e to the, so here I'm differentiating, so e to the x, no, that's fine, so e to the x cos y. I should get a minus sign somewhere. So when I differentiate this, here I think one should get. And the point is that this matrix is invertible whatever x and y are. Its determinant is just e to the power 2x. And F is a local diffeomorphism, but F is not a diffeomorphism since it is not, it's not, for instance, it's neither surjective, since it's not injective, or for that matter, or surjective. The value 0, the 0, 0 is not assumed by this map. And it's not injective because of the periodicity in the y variable. So one can have local diffeomorphisms which are not diffeomorphisms. Right. All right. So let's stop here. In the next lecture, we'll get an important way of using the constant rank theorem. We'll get an important sort of procedure of generating a large class of submanifolds. So we'll stop here. Thank you.